Okay, so David.
Yeah, so thank you for having me at this nice workshop. I'm David Trestini at the University of Southampton. So I was asked to talk to you about prospects in post-Newtonian theory and gravitational self-force. But I've been doing gravitational self-force for only 1 year and I have 15 minutes. I've downgraded my talk to prospects in post-Newtonian theory, but I'm happy to talk about self-force with whoever's interested later on. So as Harold presented, we're mostly interested in binary, let's say, black holes or neutron stars, which come, they merge, and this process has 3 stages, an in-spiral, a merger, and a ring-down phase. And post-Newtonian theory will be mostly interested with the in-spiral phase, where the 2 bodies are well separated, have a small velocity, and so you have a perturbative parameter you can expand it. So the main, one of the main key useful things in post-Newtonian theory is that you have the Viro theorem, which is that for a bound system, if you have a small relative velocity, that automatically implies a large relative distance and vice versa. And the starting point is simply Newton's law of gravitation, where you describe the acceleration of each body as, in terms of its position with respect to the other and the mass of the other body. And from this, one can then extract gravitational waves using Einstein's quadrupole formula, which at leading order is given simply by the time derivative of the quadrupolar moment of your motion. And so you see that your quadrupolar moment is kind of what you would expect it to be. You have your masses, your positions, and then you take derivatives using these equations of motion, and you get gravitational waves. Now, for a system which is not extremely well separated, but relatively well separated, you can still do this, but then you have to add corrections in V over C squared. These are called post-Newtonian corrections, and a correction of order V over C to the power 2n is npn. So that's why you can have half integer pn orders. Okay, so I'm first going to do a review of what exists in the post-Newtonian literature today. So the starting point, of course, is if you define the relative position of your 2 bodies as x, your relative velocity as v, and your relative acceleration as a, most of the information about the motion, or all the information about the motion, is contained in the equations of motion. These are differential equations which relate your acceleration to the positions of the 2 bodies and the masses. And conveniently, we tend to divide these equations of motion into a conservative piece and a dissipative piece. So the conservative piece is the piece of the acceleration which is time even, which ignores dissipation, so ignores gravitational waves and the radiation reaction. And it only comes in even powers in 1 over c. So you have 0pn, 1pn, 2pn. And this derives from a Hamiltonian. And so there exists a conserved energy in the sense that if you take a time derivative of this conserved energy with respect to the conservative acceleration, so here I insist that here we're taking derivatives not with respect to the full acceleration, but just the conservative one, then you get 0. And you can also construct a conserved angular momentum. So at 4th post-Newtonian order, what has been found is that you have a subtlety, which is the dynamics become non-local due to tail terms. That means that the equations of motion that you had before are not ODEs anymore, but integral differential. So the acceleration at any time depends not only on the positions and velocities at that time, but also on the whole past. So this complicates things, and one of the consequences is that the conserved energy is not the on-shot value of a Hamiltonian, but you can still construct one. So what's the state of the art? Ignoring spin contributions for now. So dynamics would be described either by the acceleration or by the Hamiltonian, and there's broad consensus now at 4pn using different methods. PN, MPM, ADM, and EFT. I think we have Ricardo who's going to talk about maybe similar things later on today. At 5pn, there are various results which are not all in agreement. So I don't think that we currently have a consensus on a 5pn equations of motion, but that might come soon. And there are 6pn partial results. Okay, now that we've talked about the conservative dynamics, we want to have, we're interested in the dissipative dynamics. So dissipative dynamics are time odd, and they contain purely, pure dissipation, which drives radiation reaction. This comes in odd powers in 1 over c. So it starts at 2.5pn. That's the order of radiation reaction. But then at some point at 4pn, you hit the tail. And so you start having, even PN terms because of this dissipative non-local tail. So one question is, does the split still continue at higher orders? Can you still have a clean split between dissipative and conservative effects? That's, I think, more kind of an open question. Okay, so we're interested in radiation reaction. So this actually has a link to the flux balance laws of conservation of energy. So there's a certain notion of energy, which is going to be the binding energy, which is related to the Bondi energy, something you can measure at Scri+. And this is such that if you take a time derivative of this binding energy with respect to your full acceleration, conservative plus dissipative, then you recover the fluxes, the energy lost by your system. So this energy loss would naively be the energy at infinity, some sphere at infinity. But you also have to take into account the fluxes at the horizons of the black holes, because this is not going to come back. And this binding energy is very close to the conservative energy, but not exactly the same. They differ by what we call shot terms, which formally enter at 2.5 post-Newtonian orders, and can be interpreted as reversible exchanges of energy between your system and the field, so over an orbit. Okay, so this kind of gives you an idea of the workflow in post-Newtonian theory, which is that you're typically first interested in getting the conservative dynamics. Once you have these, you can compute the gravitational radiation. And then from this, you can obtain the radiation reaction, the odd parts in your acceleration. And then it feeds back. But it's since you have a hierarchy, you can actually always do this. So with your Newton's law, you can get Einstein's quadruple formula here. This is the fluxes, and this is the accelerations. And from the leading order quadruple formula, you get the 2.5 PN acceleration, et cetera. And this is actually linked to the way we do the computations. So in the near zone, we'd perform, near the matter, you'd perform a post-Newtonian expansion, which expands in retardations. And so this actually blows up at infinity. And on the other hand, in the exterior vacuum zone, you can do a multipolar post-Minkowskian expansion, which is valid in vacuum and blows up because it's a multipolar expansion when R goes to 0. And these two things are defined, solved up to a homogeneous solution. And you can choose both these homogeneous solutions by asking that the two that the limit asymptotic structure when R goes to 0 of the exterior zone matches the asymptotic structure of the near zone when R goes to infinity. So this is kind of like a boundary condition. So the status of radiation is that a group obtained 4.5 PN fluxes like 2 years ago. So the only other group which obtained, which has confirmed these results is this group here that got the results at 3 PN. And many collaborators actually in this room have worked a lot on fluxes of angular momentum, which is known as 3 PN. And so concerning the waveform, so this is a bit complicated because the state of the art depends on each mode, and it would be too long to present. But just remember the highest order known for a mode is the H22 mode, which we got at 4 PN in this case, or circular orbits only. Now, considering the radiation reaction, again, so there was broad consensus at 3.5 post-Newtonian order, and as well as 4 PN. Now, at 4.5 PN, there was these two works which basically extracted this radiation reaction component in the same way as here. So this one used flux balance laws, and this one used something which was more supposed to be more first principles. But they omitted one thing, which was that at 4.5 PN order, you have a hereditary contribution, which enters in the center of mass frame. So this can be understood because when you want to give your acceleration in the center of mass frame, the center of mass frame is not defined only with respect to the matter. It's the system matter plus radiation. And so you have these non-local terms which come from integrating the fluxes, which you have to include. And this, you have this. It's local, but when you switch to the center of mass frame, you create these non-localities which weren't considered. So this is something we did completely in this paper. And so this is all very linked to gravitational recoil. Okay, what about spin, which I've ignored for now? So at 4 PN, basically the complete spin contributions are known in all sectors: spin orbit, spin, cubic in spin, and actually quartic in spin. Quentin-Henri has done some work completing the oscillatory waveform with spin, and I've worked in this paper here on getting the memory waveform with spin. Saket, who's in the room, has worked a lot on horizon fluxes with spin, and you have many, many such results. So now that we've found our equations of motion, we could say, okay, we can stop here and we can just integrate these equations of motion numerically, plug that in, get a waveform. So that's true, but this is slow because you need to resolve the orbital timescales and the radiation reaction timescales. So you have to resolve all these timescales in your ODE, and a better approach, when possible, is to find an analytical solution to the conserved equations of motion. To the conservative equations of motion. If you have such a solution, you can then only evolve numerically your constants of motion due to radiation reaction, so that's much more efficient. And at leading order, the solution is known. It's the Kepler parametrization, which has been known for since Kepler, basically. It's written in terms of this eccentric anomaly and parameters, which would be the eccentricity. This is how you would define it: the eccentricity, the periastral advance, etc. And you can then find corrections to these equations at different post-Newtonian orders. And the status is that there's a complete parametrization at 3pn for eccentric orbits. And at 4pn, there's, so actually a lot of people here have worked on this, and at 4pn you have a partial parametrization, which doesn't entirely include all the hereditary terms. In this paper to come, I'm getting, it's not complete either, but it would be at least the fundamental frequencies entering this parametrization at 4pn, including tails. And you have a lot of work that has been done as well for hyperbolic orbits. Right, so if you're confused about all these things and you just want a result, so I've created this Git repo, PNpedia, which essentially has the goal of compiling all these useful post-Newtonian results. So here's a website. I encourage you to check it out, to use it, to verify it. If you've already coded things up, you can cross-check, to populate it if you have extra things which aren't included, and please to cite it. So talk to me about this if you're interested later. Okay, so in the 2 minutes left, some prospects. So I'm just going to go over a few difficulties which are going to plague higher order post-Newtonian computations. The first difficulty is something in the near zone computation. So what we have is a metric, G00, which we want to express in terms of the positions and velocity of the particles. And this is parameterized by these potentials. And these potentials satisfy some wave equations, which you have to solve. At leading order, it's easy. You have a flat box operator on your V, which is sourced by something compact. Just do a Green's function integral, boom, done, you have your result. But then you iterate. So you have another potential at higher order, which would be the W, which is sourced not only by compact terms, but also by this potential itself. So V goes as 1 over R. So you have 1 over R squared. You have some derivatives there. But essentially, this is defined everywhere in space-time. And so if you do a classic Green's integral on it, this thing blows up. So you have to regularize this. And these computations are quite complicated. And as you iterate, it gets harder and harder. So you have some super potential techniques to treat this. But it's not guaranteed that this always works to all orders. Because you have to do integrals over basically the position of the first particle, the position of the second, field point of a first particle, field point of the second one, and R1, 2. So yeah, that's one difficulty. The second difficulty I'm more familiar with would be in the exterior zone, in the MPM iteration, where you're basically iterating the vacuum equations in small h, in small perturbation. So at quadratic order, you have these non-local contributions which arise, which are tails and memory. So tails, you can see them as gravitational waves trying to escape the potential generated by the binary. Whereas the memory, you can see it as a gravitational wave which re-radiates gravitational waves and interferes with itself to create DC terms. And at higher order, you have lots of more complicated terms which we actually know how to do relatively generically. So quartic tails, and there's been lots of work to get this to very high order. So these are lots of, kind of complicated, but we know how to do it. But then at cubic order, and this was my PhD, but you have a very complicated tail of memory term. So these are complicated because you have two dynamical multipolar moments and one static, and it's cubic, so one static, one. So the integrals here are much, much harder. And we managed to get this, but it was only tractable after some magic simplifications we got at the end, which are kind of resemblant to some of the simplifications you get like in particle physics. You have like like polylogs which all go away and stuff like that. So the question is this going to be possible to continue the higher and higher orders? Okay, I'll skip this one. Actually, let's just take 1 minute. So now another problem we have is if you have a metric, G mu, we also often have to evaluate it at the location of that particle. And you can do Hadamard regularization, but this tends to be ambiguous. So the correct way to do is dimensional regularization. But this tends to be very hard. So we might import, could be interested to learn from EFT how to do these things more systematically. And finally, this was all about how we push PN computations to higher and higher order. But one more important thing, I think, is how we can solve these equations of motion for more generic systems. We want to try to get, cover the parameter space. And so, for example, for precession, very little is known. There's some works at 1.5 PN and 2.5 PN to find solutions to the equations of motion with precession. This is linked to separability problems, and so this is something I think which would be interesting to solve. So to conclude, PN has been making steady progress, and we've always found that PN orders have always improved their accuracy. I'd say that our focus now should be to expand the parameter space rather than going to much higher PN orders. And so, we have challenges, but I think we can deal with them. So I'll take any questions.
Thanks. Thanks, David, for a very nice summary of these methods. We have time for 1 or 2 questions.
Yeah, I have a question. You also mentioned in your conclusion slide that we should focus more on we should not focus more on the expansion of more PN order. I have a question on that. Like most of the waveform ICs, for example, Taylor F2 and other waveform limits at 3.5, and they have recently added also 4 PN. So why 3.5 is good enough? I myself also try to do this, like going from 3 PN, 3.5, 4 PN up to 4.5 and see the results of the parameter estimation posteriors. So how do you choose?
Okay, so I mean, I'm not saying you don't have to push PN orders, but one temptation would be to focus a lot of energy on going for circular orbits, non-spinning from 4.5 to 5 to 6. I mean, this is interesting, and this is something I like to do. But when you see that on the other hand, we're not able to have a model, like our models for eccentric processing is 1.5, 2 PN. And these are things that we expect to see with LISA and all that. I'd say that it would be, first, the priority would be to try to have a generic waveform up to 4 PN, catch up with the rest before we go higher orders for just circular. So, because in future detectors, basically, I think circular orbits are going to be more of an exception than the norm, because you don't have time to circularize, and we expect to see more generic systems.
Okay, thank you.
I had a question on this extended object effects. As of now, the extended object effects enter at 5 PN, right? Because of tidal. So before some months, so hi David here.
Okay, sorry.
Yeah. Yeah. So as of now, the extended object effects enter at 5 PN order through tidal interaction terms and all. But recently, before some months, there was a work by Clifford Will where he suggested that the extended object effects could enter at 2 PN or 3 PN, but it has not been somehow not looked at much. So what is your comments?
That's this paper here. My take is that it's just that they haven't managed to do it. That's what I'm saying. So it's something which is, I'd say that doing, the method he uses trying to keeping all these things, it's basically intractable. So maybe someone will do it at some point. I don't believe it's actually non-zero. I think they just haven't managed to show it's non-zero. So yeah, I think Cliff was especially, raising this to have someone to work on it, and to create interest rather than actually claiming that this thing is non-zero.
Yeah, yes, I think it will be important for neutron star binaries that if it enters at 2 PN.
Any question up there as well?
Okay, thanks. You can move to the, okay, right. Sorry, can you ask it over tea or something? Because it's
Okay.
already in 5 minutes. So thanks, David. Let's thank David once again. We move to the